This session is on radar defense. This actually is not a radar talk in the sense of an actual radar. This is rather a talk on hardware, if you will, that would go into any kind of electronic system. Quite frankly, this would be more typically in civilian applications with 5G type things, but certainly radar people would use it. What I want to focus on here is software, actually. I work for a software company, AWR, and I wanted to explain some of the challenges that we go through in order to be able to create products that you can use so you can create your systems. And in particular, if we look at the world of defense electronics, the world of commercial electronics, this is a 5G example here. What we're seeing is a lot more integration, a lot more sophistication, as you're aware, both for cost and performance. And we in the software industry have to respond to that. So I want to show you, and many of you, if you're not designers of software, you just use software to work on the things you care about. And I kind of want to show you some of the challenges that we go through and how we've overcome those challenges. So what we're seeing here in particular, this is an example of a 5G module. This is, and if you haven't heard of 5G, you must have been in a cave for the last couple of years in this field. 5G is going to do everything. Heal the sick, raise the dead, as the blues song goes. So it will be a miracle. It's coming very soon. People are prototyping, and this particular one, I just grabbed this out of Microwave Journal, actually. This is, for example, IBM and Ericsson. And what you're seeing there is an 8x8 patch array, so 64 elements that you would typically use for integrated circuits, MMICs. This particular one, they're using silicon technology. I've seen ones using gallium nitride technology combinations. I'll show you a picture in a minute. And so what we've got here is they like this because it's low cost, small size, and they can easily deploy it. Well, we in the software world have to support that kind of design. So what I'm showing you here is this is a prototype, a mock-up that we are using internally at the company in order to show you the kinds of things that we would need to support. And what you're seeing there is many different technologies. We have a gallium arsenide power amplifier there. You're seeing some silicon germanium power amp. Of course, a lot of your control electronics, etc., would be silicon. Various surface mount components. Very popular right now in terms of phone technology, mobile technology, is BOS SAW filters. They've kind of revolutionized the phone market, and you see that. Oddly enough, actually for 5G, just as a little aside if you didn't know this, so BAW and SAW technology have revolutionized the phone markets. They allow tremendous filtering of the bands. So you have like an LTE, for example, with 32 channels. And they can do that. BAW and SAW are not going to work well for 5G. They start petering out after a few gigahertz, and by the time we're at 28 plus gigahertz, like they're talking about, they won't work. So they're going to need a different filter technology. So that's something to watch out for. They have ideas, but there's going to actually be, I think, a big shift in how they do these. So that BOS SAW filter probably actually won't be there for 5G. Okay, well, I'm a software designer. I've got to be able to make it so you people can actually simulate that thing. So let's see some of the things you're going to want to do with it. Well, first of all, you're going to want to use, obviously, several different technologies here: gallium arsenide, gallium nitride, silicon, board technologies, module technology, so for example, Illumina, something like that, LTCC. I've got to support all that, so what you're going to have is multiple PDKs or libraries. If you don't know what a PDK means, it's a process design kit, and it's exactly the same thing as a library. It's a cadence term. And the point is they have different models, they have different stack-ups, different everything, even different units possibly. Okay, so there's quite a lot of different stuff there. You need to use all those. We need to figure out how you can use them all. That's a problem. And you want to use them all at the same time. So that's even a bigger problem. And so, for example, in electromagnetic simulation, you're probably worried about transitions from one technology to another. We internally call that a multi-technology problem. So, for example, from your board to your module through BGA balls, that's 2 technologies. Module to a chip with bond wires, that's 2 technologies. Might have 3 technologies. So you got to support all this. Other challenges that you're going to do is you're going to use different simulators. Typically, you're going to use time domain methods for a lot of, especially your silicon chip work. And you are going to use frequency domain methods for the power amplifiers. So there's 2 different circuit simulators. And it doesn't get easier. You notice down there it says modulated domain. So one of the things we need to support in these types of designs is you're in modulation domain is, of course, we have a carrier. The primitive example would be AC, and then we modulate the carrier. Well, by the time you're going to these sophisticated encoding schemes like LTE, the carrier is deeply modulated, and so and it is not periodic. And so you'll have these modulation depths of 6 to 1, and if you try just using harmonic balance, you're not going to make it. If you try using just SPICE, you're not going to make it because you're following the carrier. And so you need more sophisticated simulation methods. And they have these hybrid methods they use now. So we have to support that. And I already mentioned the different EM technologies that need to be supported. I've already mentioned a bunch of this, so I think I will skip over the details of this slide.
Quick question. Did you call that a multi-chip module, that arrangement you have right there?
Yes. Yeah, that would be the philosophy of a multi-chip module. So again, what people are doing here with multi-chip modules is you as the, take a radar example, this is radar session, you would be getting this module that would have several chips in it, possibly a phased array, et cetera, and you're just going to plunk that down into a larger system of some kind. It's easy to swap in and out, it's cheaper, and life is good. So yeah, that's the way everyone's going. I'm going to skip that slide. Okay. I want to talk about EM for 2 reasons. First of all, it's one of the bigger challenges with multi-technologies. And second of all, it's actually something I know something about, so good combination. Basically, in a nutshell, as I mentioned earlier, what we have to do is we have to support multiple technologies in the EM simulator. You've got multiple PDKs libraries. You've got a board library, a module library, a chip library. You want to throw all of those into one simulation. You can see an example here on the lower right, a simple example. That's actually a MIMIC chip, 1 technology, in a quad flat pack package, 2 technologies, on a Duroid board, 3 technologies. How on earth in EM am I going to support all that? And you can do it, and the trick is hierarchy. So what we do in the software, the way you don't go crazy on this, is you do not have one layout and you're just dragging in from all these technologies because you'll go nuts. You'll never keep it organized, and you won't know what to do. So the trick is we actually have subcells, and each cell has 1 technology. And I'll show you a picture of this in a minute. And then when you put the thing together, that's when you get the multiple technologies. So you're using hierarchy in the layout is the trick. And then, of course, when it finally goes to the EM simulator, we smash it flat, and off it goes to your simulator of choice. So that's how you actually have to support this. I don't want to spend too much on this slide. I mentioned quite a bit of this. The libraries I mentioned, the multi-technology. The big one I haven't mentioned yet is another challenge is you're probably going to have several different EM simulators, and we have to support that. Now, we have our own simulators, of course. We have a finite element and a planar simulator, but you may want to be using someone else's. So HFSS, CST, these are common examples. And fine, but we have to be able to support that. So when you ship it out to those software, we want to be able to do that. And again, the multiple libraries, and so we have to do that somehow. And we want to, as we use these different simulators, to keep everything the same as much as possible. I don't want to have different layout environments, et cetera. And just to give you one example of a challenge there, as you design the software, a finite element simulator is 3D, of course, doing 3D shapes. A planar simulator is planar, and normal circuit layout is planar. So how do you do one layout environment when you have a 3D and a planar? I'll show you what we did, but there's a real challenge. I'll skip most of this slide. It's half the problem here is getting the EM result. Have to use it easily, so you get into things like data sets, not our focus. Okay, let me talk a little bit more about this EM concept and address that question very quickly of how in these multi-technologies do you work with 3D and 2D in the same layout? That sounds impossible. And part of it is, I mean, I'm not pretending that we can draw arbitrary 3D shapes in a 2D layout, but I can move library cells in that are 3D into a 2D layout. And the trick is here, for many of you working on chip module boards for your systems, and people go, well, I need a 3D simulator. I use a 3D simulator. And you do. But what are you drawing in the 3D simulator? Are you doing, well, of course, this is a radar session, so you might be working on the front end of an F-22. But for many of you, it's probably bond wires, balls, SMA connectors. These standard transitions from one technology to another. There's probably about 10 shapes that you ever do for most circuit designers in 3D. So let's just have a library of those shapes, drag them in, and 90% of the time, you're there. You never even actually have to go into the 3D. Of course, if you need one, we do have a 3D editor, but the idea here is why are we working in this complicated 3D editor when most of us don't need it? So that's the secret. I've been through most of this slide. Hierarchy is the key, and a picture's worth 1,000 words. This is another example of a flip chip that we're supporting with multiple technologies. And there you go. Here's the secret. You see on the left there? That's your layout cells. And you'll notice at the top level it says board partial package. And you see that full chip? Those are different technologies, and one is a subcell of the other. That's how you do it. Okay? And then of course, we smash it flat. Across the simulators, you want to keep everything as much the same as you can. Here's the stack-up block. We're trying to use the same things like stack-up blocks, materials. The different simulators have different ports and stuff. We try to keep the look and feel as much the same as we can. Sometimes you can't. Some simulators, if you're used to 3D simulators, you're using things like wave ports. Planar simulators don't have those. But as much as possible, as you can see from this picture, this could go to our simulator, to HFSS, to CST, and we're trying to keep that all the same. I already mentioned the 3D cells. Here's some pictures of them. You'll notice on the right you see a BGA ball, you see a bond wire. Those actually, I never draw them. I just drag them in and place them, because that's probably what you're mainly going to be doing in 3D. On the bottom there are a couple vias. Those are coming from the library. I never drew those, so I'm using the PDK, and then off to the simulator. One other thing that we do here very quickly, very common in these libraries that needs to be supported in software, There are a whole lot of features in EM when you simulate that are needed mechanically in the drawing that you don't want to simulate because they just take up a lot of cells, they waste a lot of space, a lot of time, and longer to simulate. And so we typically simplify shapes, and we have rules to do that. Now, most libraries, modern libraries, have these shape simplification rules. And I just wanted to show you an example here with multiple technology. It's a little hard to see, but the vias on the board have become squares. They've simplified them to squares, okay? I get customers all the time on vias, and I'll say, let's make it a square. It's quicker to simulate. And the customer goes, but they're round. And I go, it doesn't matter. It doesn't matter. Well, what's your technology? And the guy goes, 1 gigahertz FR4. I go, if you take the manufacturer and you have them make square vias instead of circles and your circuit doesn't work, you got other problems, okay? If you're grounding vias, if that really matters, because you first of all have 2 mil tolerance on that board. And so, you know, anyway, squares, okay? And I don't want to say you always can do that. If you're on thin film at 96 gigahertz, please don't make the vias squares. That's what you're paying for, okay? On the MMIC, and it's hard to see here, the MMIC, the vias have become octagons. There's actually different shape pre-processing rules going on, okay? I'm going to skip this. I'm going to skip. This example was of a package, and the interest here was just to summarize quickly, because I do want to get to the antennas. What happened in this example is they actually just simulated the front end, what you see here, not the whole package, because they wanted the launch. They wanted, and it's a lousy launch, but they wanted to see the launch. And then they said, maybe we should simulate the whole package. So they took the boundary and put it around the whole package. And you see the difference in that big whopping dip there is because there was a package resonance. And it's a quad flat pack, no lead package. They're notorious for resonating, and experienced designers like yourselves know that you have to ground them very well. And typically they'll have grounding in the middle of the package. This one didn't. They got a resonance. And you never would have seen it if you only had simulated the front end. So,
Like a box mode resonance?
So what happens is they in this package, you know, it's off the ground well, it's a flat pack, but there's a cavity in it, and they just only tack down the ends, and so they got a half wavelength resonance. And so what you do in real packages like this is you got to make sure you tack down the middle of the package, and then you don't get it. I think I believe when you buy commercial ones, they usually, you know, have a solder in the middle. Now I'm going to skip this. I'm going to skip this. I'm going to skip that. I'm going to skip that. I have a lot of slides. I can go on for days. This is the third-party vendors. And let's get to the antennas, last part of the talk. It is a radar talk. We did have antennas in the title, so let's talk about that. So another challenge that we have here with antennas is, it's one that you may not be, being in the software business, we're aware of this problem, but you may not be, and so I'm going to give this to you. So the obvious thing you're aware of with antennas, so let's take this antenna array, is you have to probably simulate them in an EM simulator. And so you go to EM simulation talks, and people are doing their EM method, and they're doing the phased array, the horns, whatever. And you know that, okay? And that's not what I'm going to talk about right now. Here's the problem that we have in these array problem, with these arrays. So you're making this array, and the array is going to be scanned, okay? And certainly for radar, they do this. Commercial systems, 5G, that module I had showed you earlier, they talk about scanning these things. Much more information can be carried in a tighter area, more efficient use of power. So they scan the array, and so they have different ways to do this. But behind those elements, if it's a transmitting array, are power amplifiers. The example you saw with the Ericsson IBM, they had power amplifiers somehow behind those elements. Okay, fine. Well, the trouble is power amplifiers are highly nonlinear. And so what happens is, if you design these things, as you're well aware, their performance depends on the load. okay? And so people do load pole, and you got to get the right load. Well, so they attach, in this example, say 16 power amplifier chips, 16 element array, 16 power amplifier chips to this array, and you say fine. And what happens when you start to scan it? So you're changing your phase and amplitude through your little phase shifter at each element. And this thing scans, and guess what happens? The load to each element changes. Now the power amplifier has a different load, and the performance goes down. So all of a sudden you're scanning this array, and you get horrible degradation or bizarre power in some of the elements. It's not because of the antennas, it's because the load to the power amps has changed, and that's bad. So as a designer, you need to account for that. And traditionally, the way you do it is you EM simulate the phased array. I believe the next slide. No, I'll stay here. In the phased array, what you do is you take an angle, you get the S parameters, so one EM simulation. Then what you do is you go ahead and just excite all the elements with just currents, voltage sources, current sources. Then you see, you note the phase. Then you run over to your circuit schematic. You have a load with that phase. You see what the power amplifier does. Then you have to adjust the power amplifier. Then you go back, scan, and readjust. And you're going back and forth, and it's a horribly painful process. It's not, you don't have to be Einstein to do it, but I mean, it's just really painful. So one of the things that in the software industry we have to deal with is how do you do the interaction between the antenna and the power amplifier in the module. And we have a way of doing that rather than doing it manually. We call it in situ, like S-I-T-U, for inside the circuitry. And this example shows that method. See here, this was the antenna in the world of electromagnetics. This is the amplifiers. There's 16 of them there. And where that blue, well actually where the blue circle is a Wilkinson dividers. And there's 16 inputs to the array after they go through the little phase shifter modules. Okay. Here's one of those little modules attached to the elements, and inside that we have a phase shifter, an attenuator, and an amplifier. And you see the mimic. This is the two-stage mimic gallium arsenide technology driving each element in this example. And that is, again, the power amp. It's nonlinear. And so, so as you change that phase and attenuation, you have to account for the changing load of the power amp to get the performance correct. And we have coupled those together. That's technology we have developed. And this is an example of this where they're actually showing some load polling. And I won't go through all the details of this. But basically, as the antennas scan, these load pole curves would change, or not the load pole curve, but your point on the curve would change. And the designer can account for it. Quite frankly, this design worked out pretty well. There was very little effect, which is good. That's what you'd want, but okay. All right, so as we scan it, the loads change. We account for that in the power amps, in the design and the software. The other way around now that we know the power amp performance and typically you're using, for example, a circuit simulator like harmonic balance for power amps. Now that we know the power going into the elements, we can see now what the actual power in the array, in the pattern is, right? So we're going now back to the S parameters, we're inserting power, we're figuring out how much power there is, and we actually, this is an example of the beam steering. As we steer it, the power amplifier performance at each element is changing. You have to account for that. I was talking about the pattern. So here's a pattern. Well, actually, to finish it up between the circuit and the electromagnetics, since I have the pattern here, I can now optimize the pattern. And so what I can actually do, those are optimization goals, the blue ones. You want the pattern to go through the little, the gap there, and your side lobes to be below a certain level. And you actually, for example, can adjust the power amplifier performance, et cetera, with the optimization. Okay? So in conclusion, I say 5G here. I'll say radar too. It's part of, after all, one man's 5G is another person's radar. It's all electromagnetic waves coming out of antennas, isn't it? You're going to be integrating antennas and circuitry a lot more. I'm in the software business. I have to support that. Some of the challenges then that we are dealing with are multiple PDKs, libraries, technologies, and the way we're handling that is, as you can see, through the trick of hierarchy at the circuit simulation and the EM level. Another challenge, if you are integrating the antennas, the circuitry besides multiple technologies, is the circuit and the antennas talk to each other. And to do that manually, especially with these power amps, et cetera, and the loads, is a nightmare. And so the software has to support that interaction, which we now do through the in situ technology. Okay, we're out of time, I believe, and I'm out of things to say. That worked? Okay, thank you very much.